All right, so I'm Stefan Wild from Oregon National Lab, and it's my pleasure to introduce the public lecture and final plenary talk at what has been a remarkable PASC 19. We're all in for a treat this afternoon because Professor Keren Bergman is here. Professor Bergman is Charles Batchelor Professor of Electrical Engineering at Columbia University and received her BS from Bucknell and her MS and PhD degrees from MIT, all in electrical engineering. She's a fellow of the IEEE and the Optical Society and serves on boards such as the U.S. Department of Energy's Advanced Computing Scientific Advisory Committee, where she oversees things like the deployment of the first 2 exascale machines in the U.S. As director of Lightwave Research Laboratory at Columbia, she leads research programs on optical interconnection networks for advanced computing systems, data centers, and chip multiprocessor nanophotonic networks on chip. Her talk today is entitled Flexibly Scalable High-Performance Architectures with Embedded Photonics. So please join me in welcoming Professor Bergman.
Thank you, Stefan. That's great. Thank you. Thank you so much for the introduction, Stefan. And I just want to give my heart-warm thank you for the organizers for inviting me. It's been such a pleasure, such a great experience to come here. And I just keep remarking on how seamless the organization here. So thank you. Hats off to the Swiss, I guess. So this will be a slight change probably in some of the other topics you've heard over the last 3 days. My area of focus is on photonics and optical interconnection networks, but with applications to high-performance systems. So I'm hoping that this will inspire some of your imaginations in terms of where technology is going. So this is probably very familiar to everyone here. Some of the trends and challenges of high-performance systems. So if we look at the top system, at least as of a year ago, the Summit, it's a very powerful, over 122 petaflops. Of course, it's LinPack, and we can argue about the utility of that. But nonetheless, this is an extreme achievement, very top-performing systems, and of course, we're on track to exascale. In fact, on some data analytic applications, this system exceeds the exa-op. But these are not double precision; these are half precision. So you can kind of argue about the validity of that. Nonetheless, this is a very powerful and very energy efficient system. So the entire power consumption of this sort of top 500 supercomputer is 13 megawatts. And so, that's 13 megawatts, everything, operating at least a LinPack application. And so in terms of power efficiency, it is also ranked as number 5 on the top green 500. So those of you, of course, you know that we have the top 500 best performing supercomputers in the world, and then they take the list and they reshuffle it to rank the most energy efficient supercomputers in the world. And that's the green 500. So at least as last year, that it's very impressive that the top system was also one of the top energy efficient systems. It's a very interesting sort of architecture because the number of compute nodes is quite low for over 100 petaflop machine, right? We only have 4,600 or so nodes. And so we understand that these nodes are what we call fat nodes. This is with a PH, not F, just to make them cool. So they're very powerful nodes. They have a lot of computation power. They have GPUs as well as CPUs and so forth. However, despite the fact that they're very powerful, the I/O bandwidth, the communication bandwidth that we have available to us off this very powerful compute node is extremely low by comparison. 200 gigabit, essentially, with some Mellanox, some Mellanox InfiniBand I/O. So if we look at the kind of the ratio of the compute power versus the communication, we'll see that there's a huge and growing disparity between those capabilities. And just to kind of put some numbers, if we want to get to the exascale, so 13 megawatts is still a very large number. And just kind of an order of magnitude, a megawatt a year is about $1 million. So just kind of to turn on the system, it's not an inexpensive thing. And so there's going to be a limit to how far we can scale these in terms of energy, not just from the energy side, but also from the dollars side. I mean, can we have a 200 megawatt facility? Okay, that's fine, but you need to pay $200 million a year just to turn it on, just to turn the lights on. That's without the people and anything else, or the machine. So the money is also, the cost is a very important aspect. So when we think about going to exascale, which will be another factor, and we're definitely on the way there. I think we're going to get there in another 2 years or so. We want to be perhaps within 20 megawatts, maybe more, maybe 50 megawatts, but this is the sort of energy efficiency that we need to get to in order to do exascale, at least within 20 megawatts. Okay, so now that we have some of these numbers, what we did was we sort of looked at the trend in performance versus communication of the top 10 of the top 500 systems in the world, right? And so what we see here is, in the blue curve, is the node computational capability. And it's very obvious that the computation capability of the individual nodes in these high-performance systems is growing very fast and will continue to grow, because even though it's quote-unquote the end of Moore's law, the density that we can shove transistors together is not necessarily slowing down. So this is growing. However, the communication or the I/O bandwidth that's available to us per node has been relatively flat, over the last almost decade. And so if we look at the ratio of, the compute capability, the average compute capability of the node versus the communication capability, that ratio of the bytes per flop ratio, if you will, bytes of communication per flop of computation, has been going down, and in fact going down, very fast. So just before the summit, the Tihahu Light, the Chinese supercomputer, was the #1 ranked in the world. So this was back in 2017, and its byte per flop ratio was 0.004. Those of you that might remember the good old days, we used to design systems that were actually quite balanced. It used to be the rule of thumb that we had 1 byte of memory per 1 flop of computation per 1 byte of communication. So this ratio of 1 is out the window. And then more recently, the summit is actually 0.0005. So we've gone downhill even further by another factor of 8. And how far can we really do this and still have useful computation from our systems? What this tells me is that the computation in the summit is essentially done on the node. And as soon as you get off the node with that 200 gigabit InfiniBand, not much is happening. Not much is happening system-wide. It's like drinking out of a tiny straw when you have a waterfall of computation. So it is, and so when we think about scaling, I know this crowd is very interested in applications. You think about scaling applications that really need to use the entire machine. This could be an important problem. I mean, I imagine there are some computations that are very parallelizable, fine, and each of these nodes can perform in parallel, and that's not an issue. But for anything that requires communication-intensive workloads, this becomes a very important limiting factor. In fact, some of the communication-intensive workloads on these top systems only have efficiency in the single %. Okay, so why is that? What's going on? And the story is about data movement, the communication, and the energy associated with data movement. So let's look a little bit at how the energy and the data movement balance. What is the trade-offs in terms of the proportion of system energy that's going to data movement versus computation? So just looking at the numbers, if I have 14 gigaflops per watt, which is more or less the efficiency of the summit, that you just flip around the algebra, and that's 72 picojoules per flop. If I want to look at the exascale, maybe 50 gigaflops per watt, I have to be more efficient. That reduces even further to only 20 picojoules per flop. And just to put the energy in terms of communication, we like to think in communication in terms of energy per bit. So a flop is more or less 200 bits. And so if I just kind of do some math, the 14 gigaflop per watt is 0.36 picojoules per bit. That's the energy efficiency that I can extract from that. Which is, to people in communication, this blows our mind because this is an extremely energy efficient number. To communicate over any kind of distance with, picojoules per bit is very, very difficult, very challenging. And so for the entire system, performing a computation with an energy efficiency of only a fraction of a picojoule per bit is amazing. So what's going on here? What's going on here is that there's no communications, practically speaking. So this is the order of magnitude of communication energy, what it costs us, right? If I'm staying on my little chip and I'm just talking to my SRAM locally, I'm fine. I'm in the femtojoules per bit regime. However, as soon as I start to access DRAM and high bandwidth memory and so forth, as soon as I start to move my data anything more than a few millimeters, the energy that I need to expand is on the order of 5, 10 picojoules per bit. And if I need to go across the system, it's like falling off a cliff. I mean, it really is very, very expensive. So if my entire system budget is like 0.36, or maybe in the future it would have to be 0.1 picojoule per bit, and I have to do a DRAM access, you can see how it blows away my budget. And if I miss the cache, that's a very expensive operation. So I have to be very, very careful about my communications. And in fact, what I end up doing in many of these systems is keeping everything extremely localized. And that's why we got these fat nodes, essentially, and almost no communication is happening, other than locally, very locally. And so, we've done all kinds of stuff in the computer architecture business. We've scaled performance, we've raised the cache, hit rates, improved the memory access, all of that. But it's really, the next step, or really the necessary step, is about, really improving these interconnect technologies to get something that's more energy efficient, fundamentally. All right, so I just want to go back to this top 500 list. And kind of show some of the recent trends, right? So what you see on this little chart here are the top 3 supercomputers in the world in June 2016. The top three green 500 supercomputers in the world, the most energy efficient supercomputers, about 3 years ago. So the Shubu, the Japanese, had an efficiency of 6.7, and that was the #1 most efficient system. But the Sunway was only #3, which is great. It was the #1 in the world in performance and #3 on energy efficiency. So really, they did an amazing job on energy efficiency. Okay, you go forward just a few months from June to November, and all of a sudden, the top system in the world on energy efficiency is going from 6.7 gigaflops per watt to 9.5. That's a pretty big jump in just 5-6 months. Okay, and then the rest of them are kind of lined up. Here's the Shubu, who was #1, and then kind of drops down here. Okay, you go forward another 6 months, and instead of the DGX, we have the Japanese back on top, and we go from 9.5 efficiency to 14.1 efficiency. It's rare in technology to see such a big change in anything, in any metric, in such a short period of time. We go forward another 6 months, and we go from 14 to 17, and lastly, just last year, we've gone all the way to 18 efficiency. So from 6.7 to 18.4 or so. And is it getting better? I'm not sure going forward, but it's just a huge acceleration. So more than a factor of 2.5 in just 2 years. And the top-ranked system today, the Summit, is number 5 on the Green 500. Okay, so what's been going on? What's happening underneath all these colors that I've coded here, the greens and the reds and the yellows, is that basically the underlying engine that's been improving these energy efficiency, at least so far, has been the interconnect technology. And so these are just the names of the various interconnect technology, but I just want to show you one example, which is the Nvidia example, which led to the first big jump from 6.7 to 14.1 in energy efficiency, right? What happened? Why did that become all of a sudden so efficient? What Nvidia did was they went from this geometry. You see over here, this is the GPU, the Kepler, and these are the GDR5s, the memory chips, right? And they went over that year, they redesigned everything, so now everything is sitting on a silicon interposer. So essentially, it was a packaging or integration technology for the interconnect that changed the ballgame here, right? So now you see, here's the GPU, here's the DRAM, and the connectivity, these are 1,024 data links at 500 megahertz here. The connectivity between the GPU and the high bandwidth memory is happening over a high performance silicon interposer, instead of going over these long wires, relatively speaking. So they basically went from kind of an order of magnitude 100 picojoules per bit communications between the GPUs and memory to order 10. Actually, it's less. It's like 4 or 6 picojoules per bit right now. Interesting. Okay. So the interconnect technology can make a big difference. What else is going on, which is an interesting trend, which I think we all know, is the idea of data analytics. And all of a sudden, you start to see these, those of you that paid a little attention, you notice that I had some blank boxes here. And it's just very interesting to see that Facebook is popping up on the top 500 list. Why is Facebook interested in supercomputers? Well, data analytics, right? It's everywhere. And this is what's happening in data centers. And so it's all about how quickly you can run these various deep neural networks, machine learning, AI, et cetera, et cetera. I won't go into too much detail here because I know there's many talks related to that. But just to indicate the fact that the data centers and the high-performance computer systems are essentially almost one and the same these days, because we're all driving towards the same goals with these data analytics. They've just taken over. They've just taken over the computation. So my talk is about photonics primarily, and the question that I am raising is, what can photonics, actually bring to this table? What can we do here? We know that optics is potentially, a very attractive communication technology. We have, optical fiber communications all over the world. We have optical networks. But what can we do in the context of these computing systems, to bring some of that communication technology to bear, right? So I'll remind you of these terrible numbers. And basically what optics does is it'll flatten out the curve, right? Here we have, this is orders of magnitude. As soon as you move some distance away, the energy that you expend for moving that data rises almost on an exponential level. And so what you see here is the red curve is the electronic. The blue curve is the optical, the photonic. And so the optical curve, essentially, once you generate the photons, you can propagate them with very low loss. That's just fiber optics can go kilometers, thousands of kilometers across the world. And we're talking about moving the optics, on the chip and just, across the system. So we're not even going very far, like 100 meters, maybe at the most a kilometer, 1 kilometer, within the data center. Unlike optics, the electronics, you see, this is a log curve, right? And so as soon as we start to go off the chip, every time we have to regenerate those electrical bits, we're expending a ton of energy. And so this is the advantage. It's not that, to generate the photons and receive the photons, it's the same electronics, so they're going to start at the same place. The difference is the low-loss optical propagation waveguide or fiber that enables us to flatten out that curve. So that's one advantage. It's this let's call it the distance-independent energy for data movement. So once I create the data, let's say it's at a picojoule per bit, I can move it anywhere in the system, and it's still a picojoule per bit, unlike electronics. The other advantage is the bandwidth density, and that's fundamental. That's because we have essentially bosons rather than fermions, which means that I can shove a tremendous amount of information in a very tight, in one interconnect, right? If I try to put multiple electrical signals on the same pin, they will interfere with each other, right? I can't do that. And in my pin density is gonna be very, it's limited by the interference, by the crosstalk. However, with optics, I don't care. I can put multiple wavelengths next to each other. To first order, I don't care. I can put multiple wavelengths together on the same waveguide, on the same fiber, on the same interconnect, and I can have in one sort of wire this, a tremendous amount of bandwidth density, right? So that's the other advantage. So this is distance independence and bandwidth density. It doesn't mean that optics is, easy. It's a new technology. It's hard to insert into the systems. It's also costly. We're also missing a lot of the ecosystem that we have for electronics, for silicon. So what I'm going to talk about next is kind of how do we do it? How do we bring these two advantages into actual systems? And I like to think about it sort of in a three-pronged approach, or three pillars, as we like to call them. So the first step is, you see this picture, is an optical, kind of our canonical optical link that we now can make using the same CMOS process that we have for electronics in silicon. So these optical links, essentially, both the electronics and the optical components, are fabricated in the same foundries where I can make CMOS. So I can leverage a lot of that technology. So I want to make very energy efficient links to begin with. And then, I need to figure out how do I integrate those optical links, those optical IOs, with the electronic, node, with a, and you will see here, this is a big area for us of research right now. This multi-chip module or interposer integration, just like you saw the Nvidia chip, on the interposer. What I want to do is I want to add photonics there too, so I can have the photonics directly interconnect the GPUs and the memory and going out into the system. And then lastly is kind of a new concept that we call bandwidth steering, right? Because of this distance independence of optics, I can now, my system is now open. I like to say sometimes the cache is my world. I can communicate anywhere in the system. This is a vision, it doesn't exist in reality, but I can communicate anywhere in the system without having to pay this additional price of energy. And so I can reconfigure my system so I can connect some memory that's sitting over here in this one rack to some GPUs that are sitting over there in another rack. I would never do this in today's system because, I can only really communicate locally. But optics opens up that envelope of communication. And so I can think about what I'll show you is a disaggregated architecture where I can really pick and choose the resources that I want to use with the optical connectivity. It really changes what you can do in the architecture sense. Okay, so this is sort of what an optical link looks like, right? The way that it works is there is an external laser, or the laser can be on the chip depending on there are different approaches. Our approach has the laser off the chip because we like to keep the thermal issues of the laser outside. And so this laser generates multiple wavelengths. Like, imagine a comb of wavelengths. And all these wavelengths enter the chip. And they go into this waveguide in silicon photonics where each of these rings modulates the data. So this is an optical modulator, a silicon photonic optical modulator. And the ring is adjusted in such a way that each ring modulates one of the frequencies of the laser. So, the laser could have 100 lines, and I could have 100 rings here, and each ring is tuned to modulate one of the lines. And they're all together in the one waveguide. And then, potentially, it goes off the chip, it can go into some optical switches, and then it goes into a receiver that could be sitting somewhere else in the system, wherever it's going. And in between, there are optical fibers that are connecting these modules over some distances. Okay, so the laser, right? The laser is a very, perhaps some people will say, one of the most important aspects in technologies here. And these are my colleagues at Columbia, Gaeta and Lipson, who developed this new technology. There are other groups, but this, I would say this is one of the leading comb generator technology, because it's a comb, it's an optical comb that's generated on a silicon photonic chip. Okay, it's externally pumped. You may know that silicon in itself is not a lasing material. It's maybe the worst optical material in the world, but it's what we have with CMOS, so we're kind of stuck using it. It doesn't have a direct band gap, et cetera, et cetera. So we try to do all kinds of tricks, but this is a laser where the cavity is on the silicon photonic, and it's pumped by an external 3.5 semiconductor laser. But the really innovative aspects here is that the resonator is designed in the silicon, it's actually silicon nitride platform, to generate a tremendous uniform comb of wavelengths. This is just showing different techniques. We can use the soliton regime. The much more recent advances have been to show that in the normal group velocity regime, you can generate a much flatter comb. But basically, we can generate 100, 200 lines of wavelengths. And this particular example, it's a Nature paper that came out last year. It was actually powered by a AAA battery. This was a little bit of a show thing, just to show that we can do it. But nonetheless, it illustrates, this kind of breakthrough technology. Okay, so that's the comb. The comb comes into to this, array of rings, right? Everything gets modulated, puts onto a single guide, and then detected. So lots of things still happen in these links. And when we design these very energy efficient links, there's a key aspect to, you really need to minimize all the optical losses. You have an optical loss budget. So there's a sort of a whole, effort, science that we do related to how we design these links. And this is just kind of a high level thing to show you that there's an important link budget. And we've been developing some various software tools, and they're interoperated with Synopsys. That's one of the major CAD providers. So basically, you can design a link to have the right characteristics, with all the components, and then with the interoperation with the Synopsys tool, you can then generate essentially a CAD file, a GDF file, send it off to the fab, and have the link fabricated. Very similar to how we do CMOS electronics. Now, that's sort of where it is, but I can tell you that it's not that simple yet, because optics is still a very early technology, and so, it's not as easy as the electronics as well. But nonetheless, we're getting there. We're getting closer and closer. So some of the things that go into designing the links. You need to, one of the major losses is the coupling to between the chip and the fiber. That's it seems like a simple thing, but it's a major issue. And so we're working a lot about creating these very robust couplers or connections. There's a lot of sort of co-parameter, you have 100 rings, how do you co-optimize everything, the size, the energy, and so forth. This is an example of a recent invention on a completely passive, we call it the plug and play, because you can take a fiber with this arrangement and just plug it into the structure, and the alignment is excellent with very low loss. So those are just some of the things that come up, and it also is very robust to variations in temperature. Okay, the other side of the design is related to the electronics. So this is the optical. You design things to be very low loss, tolerant to temperature variations, tolerant to all kinds of things. And then the driver electronics that are connected to these photonics have to be also co-optimized together with the optics for the best energy efficiency that's possible. And so this is an effort that we're doing together with Cisco. We're actually also now continuing this with Cisco, but also with Nvidia. It's interesting how Nvidia, that's a GPU maker, is now interested in photonic interconnects. And they really are. One indication of that is the upcoming merger with Mellanox. That's an optical interconnect company. But they're working with us on this particular project. They would like to. I'll show you exactly what they want to do in just a minute. But these are just kind of optimizing circuits. The point here is to show that it's not really simple there yet. There's quite a bit of sort of engineering and work that still needs to be done to get these optical interconnects, fully into the ecosystem. But nonetheless, it's definitely making a lot of progress. And we've shown that. I'll just quickly go through this, but we basically have shown that you can have at least 800 gigabit wires. So this is per wire. We're going to go to a terabit per wire very soon. Right now, we're at 800 gigabit per wire and 2.2 picojoules. Our target very soon is to get to a terabit per wire, per pin, at 1 picojoule per bit. So we still have some work to do to get there, but it's very doable. Okay, so that's the links, right? Okay, now how do we connect the links to the chip? And let me show you why this is such an important problem, or why it's an important thing to do. So one of the best, or one of these highest performing, in terms of connectivity and bandwidth and performance chips, commercial chips today is the Nvidia Switch, the Nv Switch. And so I'm just using that as an example in terms of what its capabilities are. So this is a picture of the Nvidia Switch. It has 18 NV links, 2.0s. They're probably making some improvements, but this is about a year old. And if you sort of count up the links and the linear the linear perimeter of that chip, I'm trying to figure out what is the escape bandwidth that I have right now from this chip. How much bandwidth can I actually get out with these links? And if I sort of do this calculation, and it's about, the density is about 200 gigabits per second per millimeter, which is very, very good. This is, like I said, this is one of the most advanced high-performance chips, electronic chips on the market. And I can tell you that this is very close to the limit of what's doable in terms of the electronics. Not because TSMC is limited to 7 nanometers. It's not about the feature size. It's about the heat that gets generated from the signaling electronically. And at 200 gigabit per second per millimeter, those pins, you double that, and those pins are going to start melting next to each other. So it's just physically close. I don't want to say impossible, because engineers can be very creative, but it's becoming very close to a threshold of just, at some point things just get to be too expensive and too difficult to do. Now let me show you what we can do with optics, right? Why is optics interesting here? I can have the same chip, but instead of having an electronic I/O like I do now, is put in an optical I/O, right? And with my very simple optical design, I'm not even working very hard. I'm not stressing my engineering muscles at all. I'm just putting a bunch of fibers on the chip, and the fibers are 250 microns. It's my fiber. I'm not even etching it down. I can get even better than that. I can get to 80 microns, 50 microns, but 250 is fine. And I'm just looking at what I can do, and I'm using 80 wavelengths, only at 10 gigabit per second. I'm not doing anything fancy. And I'm putting these like the 800 gig link that I showed you that we have, right? And I'm just putting them next to each other. And instead of 200 gigabit per second per millimeter, I can get 3.2 terabits per second per millimeter without stressing too much. So this is a big order improvement on the bandwidth density that I can get out of the chip. And this is the kind of factor that really can make a difference, right? Can be the game changer. I mean, when you have a new technology and you're trying to insert it, if it's a factor or two better, nobody's really going to bother, because it's just too expensive to move to a new technology or a new software or anything. But if you have this factor, right? This is a big factor. And without really, there's room to grow from here. Then, perhaps this is worthwhile. And this is the reason Nvidia is working on this with us. Okay, so what can we do with this, right? How do we get the optics into this multi-chip module? What are some of the interesting things that we could do? And the way that we like to think about it is once we get the optics into the chip, imagine an interposer that has CPUs, GPUs, a memory on it, and the optics is connected inside as well. And I can now, in the optical domain, I have 100 wavelengths. I can decide, well, maybe these 44 are going to go to this GPU right now, and then I can switch them and put the other 60 on the memory another time. And I have this flexibility to move around my optical data in this multi-chip module. It's a flexibility that I've never had before, because before I was very specific to the data rate that I was using. Once I have an electronic connection, it's static, and I'm stuck with it. But in the optical domain, I can add wavelengths, take away wavelengths, switch things around, because it's completely transparent to the data rate. And so I can think about the concept of this deep disaggregation. I can use the optics to access the resources within my module that I need for my specific application. And I'm not going to go into it in this particular talk, but one of the areas that we're working on right now is, imagine you have this heterogeneous platform, and you're trying to run a machine learning application. And it has these different phases. Like it would have the learning phase, the training phase, and it would have the inference phase, right? And so for the training phase, I can have a certain connectivity. Maybe you are maximizing the GPUs. And for another phase, I can have more memory access and just optimize the architecture to the application. And that's what's enabled here. So now comes the kind of the interesting and a little bit hard work, interesting for me, of how do you physically do it, right? How do you put the optics, what's the mechanism? Okay. I talk too slowly. So I'll kind of skip through. I'll try to speed up a little bit. So we use these multi-chip module platform, and we do a lot of technology. I'll show you this little, let's see if this works, yeah. So this is kind of, at least how we are doing the prototype. This is a 2.5D integration. You have the silicon interposer, and then you can flip chip the electronic chips right onto it. And on the same interposer, you can also add the photonic chip, just in the same way that we have the electronics. There's a lot of technology there, the density, how you do everything, and then you have to, put it into a board that you can then, for now it's just a prototype, so we have a board that we can connect to both optically and electrically, and this is just one example of the prototype that we've made. This is together with the Tyndall Institute that's in Ireland. Okay, so we do all those things, and so I just want to talk a little bit, a couple of minutes about this concept of the disaggregation, right? So in today's systems, we have the server, and the server has some memory, some processing, some GPUs, etc. And so when you connect to the server with that 200 gigabit InfiniBand, you're connecting to the server, and everybody that's in that comes along for the ride, even though I want to connect only to the GPUs. I don't want the memory and the CPUs to come along for the ride and waste all that energy. So the concept of the photonics is about disaggregating it. I want to separate the resources and then reassemble them in the way that I'd like to. And so just to kind of give a very quick example of that, what we've done is we've taken the fat tree topology, which is very common in data centers, and I'm going to skip quickly through that, but I can go into more details. And we basically added optical switches in the middle, so that now we can reconfigure the fat tree in other ways. We're not limited to going all the way up to the spine and back down again every time. And so we have much more direct links across the pods in this particular architecture. I'm going to skip through that. We've actually built this test bed. It's in the lab with these optical switches that are inserted there. And what we can show, and this is very, very simple, just a skeletonized GTC application. We can show that we can run things a little bit faster, 25% faster. That's cool. But we can even do better than that, because what the optics can do is we can flexibly keep the traffic only in the lower layers of the network, because we can make direct connections with the optics and reduce the latency even further. And so by tapering the upper layers and keeping the connections down here, all I'm showing here is we can make things even faster. So this potentially has some really interesting directions for accelerating applications. That's one. The other is the issue of fragmentation. So you guys are on the application side, a lot of you, and so the first guy that comes and puts a job on the big system, you can place it where you want them, the nodes where you want them. But the next guy comes along, and there's not that much space, and you might get fragmented a little bit. And then if you come in kind of late, we're going to put your job wherever we can. We don't care. And so you think these things are next to each other. You think your execution is going to run a certain way, but it doesn't. That's reality. And so what the optics can do is it can recreate those direct connectivity on the fragmented workloads, because this is a real system application. And so again, we've gone through and we've shown that, at least initially now with simulation. This is still ongoing work, and we show that we can get accelerated throughput, we can get better latency, and lastly, we can get much more efficient usage of the links, right? We are basically, by redirecting the traffic with the optics, we're only using the links that need to be used for that particular workload. We're matching the workload, we're matching the connectivity to the workload communication that we have on hand. And we can reconfigure it as needed. And in the end, that also gives us a tremendous energy savings as well. So, these are, again, simulations compared to standard fat tree systems using essentially current active photonic technology and electronic packet switches. And we can show that there's substantial power reduction as well that comes in to this design. Okay, so just in summary, data movement is obviously a very critical aspect, and it's going to be an increasingly difficult problem, as we really go into more scaled systems. You saw, from the beginning how the energy is just really limiting the communication, and photonics has the possibility of opening that up. It's not without its challenges. But fundamentally, the technology does have the ability to propagate over longer distances with flattened energy. It's not necessarily less energy; it's just flattened energy dissipation. And now we have some new packaging technology with 3D and 2D integration, and we can start to play around with some of these architectures. So thank you so much for your attention.
So thanks for that wonderful talk, really pushing us to think about beyond exascale. So at this time, we'll take some questions for Keren. Please. And there are microphones spread throughout, so please use the microphone that's available there.
So you progressed since last year. I think you were at ISC last year, so it's really enjoyable to see progress. There's hope.
I tried a little bit, because there's some overlap with the ISC talk, yes.
Yeah, so in the weather space, the problem that you describe here is actually worse, because we don't get peak percent of a chip, right? And so and we also want to scale across. We use the interconnect much more heavily. It's a little hard to quantify exactly how much we're being penalized by that, because there's a software piece as well, and that is significant. I guess it's unclear to me how far you're fixing one piece of it. The immediate thing comes to mind is memory. That all of these elements require energy, and the energy that you're describing is kind of the longer distance, the stuff that is the one you want to pick off first. but systems are about balance, and memory itself has got a huge drain on that. And I know you're not going to solve all our problems. We're certainly happy, but I wonder if you could comment about that as more of a whole solution.
Absolutely, that's a really important point, and we have thought about it to some extent. So an interconnect typically is, I don't know, maybe 20% of the entire system power consumption, right? 15, 20%. So even if I were able to create this magical interconnect and reduce the power associated with it to zero, I still have, the other 75%, 80% of my energy. So how do I, get that bulk, right? And so the way that we are thinking about it is, it's the bulk of a lot of the energy. I mean, we're not doing anything, we're not addressing memory or CPU specifically. We're not changing the CPU architecture or creating new memory devices. But we're changing how and when we access them, right? So, and that's when I was starting to get into this in terms of the deep disaggregation concept. So the idea that we're pursuing is let's only access the resources that we need for the exact accurate amount of time that we need them. And rather than do this oversubscription, which is done typically today in a lot of architectures, and then you got all these servers essentially sitting idle and expending quite a bit of energy. And so that's, where we're going to start to chew off some of this other chunk of power consumption as well. And that's pretty much from the interconnect sort of perspective, that's the best we can do, is provide the most optimized interconnect that matches what you need, the resource that you need for that period of time as close as possible. And the only other comment is that there's a bit of a catch-22, right? Because right now, you write your software to the systems that you got, and you optimize them to the system that you got. And so, and we go and we're trying to get traces all the time to do an evaluation of our architecture. But the traces, and the algorithms are all designed for these very hierarchical types of architectures, right? And so, at some point, there has to be a break where you really design for this very new type of architecture where you really have a much wider connectivity. And, it's exciting. It's an exciting research area. We're not there yet, but that's the direction that we're going. Yeah.
Two questions, if I may. The first one, again, relates to this thing with looking at peak and the first part of your talk where you look at gigaflops per watt. On HPL, and you argued that the energy improvement was really due to the interconnect. But we are looking at the high arithmetic density algorithm, so we're also looking, or mostly looking, at the energy improvement on the processor and right around the. In order to probe your argument, shouldn't we look at HPCG and gigaflops per watt? I don't even know now if HPCG is reporting energy, but that would test the interconnect. I mean, yes. on the package, and whether the memory really got better when we moved on package or not.
Exactly. Basically, I'm in complete agreement with you that the lin pack and the green 500, all of that. It's really, I tried to make the case that the interconnect is an important factor, but, I perhaps overstated it. It's not the only factor. There's a lot of energy efficiency improvement, obviously, that are going into the GPUs and the processors, and that's probably where a big bulk of it is coming from as well. And I also agree with you that, HPGC would be a much better metric for us, especially as we're driving towards these other types of applications, perhaps even more the Graph 500 and other, and other communication intensive. Yes, and we're absolutely, our plan is to pursue that, as well. Very much, I agree.
And to this question of, if I may, the second question.
Sure. Yes.
is about the economics of photonics, because we have, for example, in Pitstein, we have not a factory, we have a dragonfly with 3 levels. The lower 2 levels are electronic, and the upper level is optical. Yeah. And the competing system at the time from DARPA HPCS was called Blue Water, or was supposed to become the Blue Water system with everything optical. Yeah. And the reason that everything optical and the Blue Water system ended up not being the IBM DARPA HPCS result is because it was too expensive.
Right.
Or and the margins for IBM then too low in the end because the optical part was too expensive.
Plus VCSELs failing and all kinds of fun things. Yeah.
How the economics in photonics will develop?
Yes. Well, I know some things, right? I'm just a measly little professor, so I'm not an economics sort of commercial expert, but I can tell you that one of the big factors is silicon photonics. This is where things are really going, and that's kind of the game changer in terms of the economic models. In the old days of the DARPA and HPC thing, they were using VCSELs and silicon photonics. The ecosystem was not there. Now I don't want to overstate it. It's not completely here yet, but it's definitely gaining some serious commercial interest. So in the U.S., we have basically an institute where we run 300 millimeter, 12-inch wafers, all photonic. So this is an economies of scale that we never had before. This is very recent in the last couple of years. In Europe, there are also foundries, and in Asia there are foundries as well. And so that's one aspect. And then some of the big companies are getting into it. Nvidia, HPE, Cisco, and Intel, others. It's still not there. It's still not, really sort of closed the loop in terms of being a major commercial success yet. But it's marching towards that end. So that's sort of where I see things going. Yeah.
Great. And with that, I think we'll cut it off. So let's thank Keren again for that great talk.